Right, so I have my notes last three. It's not all that useful, but it's good to know that. So as I mentioned, I will change topics a little bit, and we'll talk a little bit different type of results today. And that is the simplest. There are many results of this kind, but the simplest one, which kind of started this kind of line of inquiry, is the result of Costenson and Weiss and independently Bourdieu. And to state it, you need to recall the definition of upper density, more precisely upper one density in RT first. So let me just recall it, because the definition will be very important. Like half of the proof is about the definition, other half is some calculations. So let's say we have a subset of RD. Of course, we assume it's measurable, the very measurable. And then it's upper one density, which is a little bit weaker notion than ordinary upper density. Let's denote it out of our E. We define it the following way. Is the limit, let's say L goes to infinity. Oh well, let's say Vim soup first. Of the soup for all x's in RD of the relative density of E on a cube of size L centered at X. So let me write it down. So maybe I use M for the Lebesgue measure. So measure of E intersection, let me call this cube QXL, so X is the center and L is the side length, divided by the measure of the cubic size, which is L to the D. Say L to the D. And that's it. Where is QXL? Again, this is just center of X. So you take, and this is sometimes called the relative density, and I will use this notation, the density of E on QXL, because it's measured as what proportion of the cube is filled out by the set P. And if this is positive, we say it's a set of positive upper density. Now, if this is bigger than some delta, what does it mean? It means that there must exist a sequence of cubes, but they could be anywhere in the space whose lengths going to infinity, such that in each cube, at least delta proportion is filled out by the set. Okay, so that is different from ordinary upper density, because then you assume that all the cubes are centered at zero. Here you can let them translate. All right, so we will assume. And let's make some observations. So assume delta by E, of course it's not negative, but assume it's equal to some delta which is positive. So it's positive upper density. Then what can we say? Well, if we think about this notion, this relative density on cube, if you look at the relative density of a large cube and then you cut it into smaller cubes, then the relative density of a large cube is the average of the densities of the smaller cubes. So what does it mean? It means that if you compare the maximum of the relative density of larger cubes with respect to smaller cubes, it's less than equal than the maximum smaller cubes because it's an average. So this is essentially a decreasing function, what is inside here. So if it's decreasing to some positive delta, then the following is true. That is the first observation. So then, given some positive epsilon, first observation that there exists some threshold such that the relative density of E on all cubes for every L bigger than equal L0 the relative density of E on all cubes of side length L would be less than or equal than delta plus epsilon. Okay. The second observation, of course, if we fix on L, you can choose a much larger cube on which the relative density, say at least delta minus epsilon, because that is the limit. So given L, there exists some N, and some X, which we don't really care, as we will see. So the relative density on E on this big cube, oh, much bigger than L. So now, kind of replace the whole space in this big cube, and then replace E with the intersection of E with this big cube, and within that we look at these windows, these smaller cubes of size L. And then on each cube we have some relative density. So, and we look at this function. How much this function oscillates? Okay, so now let's please say delta n to be equal to relative density on E on this fixed big cube, which I will just denote by Q sub n. It depends on X naught, but doesn't really matter. So this is the density on the big cube, which is essentially the average of the densities of the small cube, except maybe there is some wandering, but that will give very small error on average if n is much bigger than L. So, and then define, and let's say replace E with E intersection with this cube. And then we define the so-called bounce function of E prime. So you take the characteristic function and subtract and let's call this element. So basically the integral of this function over this cube is 0, or at least smaller than epsilon, because maybe there is a little bit of problem at the boundary. So it's called the bounce function. And in fact, what we will use about upper density is simply the following: that the mean square oscillation of this function, of the integral of this function over cubes is very small. So, from these two, from these two facts, if I use this formula. So then, I don't know if I should call this a lemma, but maybe I do. What is what one would be? So I claim the following, that if I consider the integral of so I average out this balance function on cubes of size L. So I consider the convolution of this with chi of L, where chi of L is just the normalized indicator function of the cubes of size L. And I look at the L2 norm squared on the big cube and normalize that, so the whole thing should be bounded by 1, because this is bounded by 1, this is a normalized function, so the convolution is bounded by 1, and this is less than a constant times not quite epsilon. Maybe comes out with epsilon, maybe just comes out with epsilon, but it is small. So let me prove this, or sketch a proof of this. So this is, because what is this quantity? So basically this is this convolution, so this is the characteristic function minus this constant. So when you convolve the characteristic function with the cube, oh sorry, there's no, this is just the ordinary cube because the convolution translates into x. So when you take the convolution at x, basically you integrate fe on the cube centered at x, but fe is the indicator function, and then in normals you just get the relative density. So this is the relative density of E on Q XL minus this constant delta n squared. So what this measure is how much the relative density oscillates on these cubes. But since this quantity is always between 0 and 1, and everywhere just epsilon bigger than its average, there should be a very small measure of points normalized where it's say less than square root of epsilon, smaller than the average. So because then when it's bigger and when it's smaller, it should balance out. So that means that this quantity must be small because there is only a small measure of points. I mean, if you normalize the measure, then it's essentially smaller, like square root of epsilon smaller than the relative density. So this quantity, say, is bigger than epsilon, a very small measure of points, so that's why you get this thing as if you get actually constant times epsilon. Okay, so why is this important? Because this defines us a norm, and this norm will control a certain quantity, which we want to do. So let me introduce a norm, and I call this the local U1 norm because it's an analog of the simplest so-called Gauss semi-norm, which is nothing else than the absolute value of the average of the function. But so let's define something. Okay, so let's say we have some cube, say q sub n, and we have a function to r. All our function would be bounded between -1 and 1, but you can define this for any function measurable, of course. And let's say we have some parameter L, which is essentially less than n, which is not the usual number theoretic notation. Here I use it less than a small constant times n. But anyway, you can define it just in this case. And then we define its norm, so-called, I denote it by U1 L norm, because there is like a U2L norm, there's a family of norms increasing complexity to be the average of the convolution with cubes to the one. Yeah. Okay. So what we have is for the balance function a small human L at some scale. So for every epsilon there exists a scale L, and then you can choose an arbitrary large cube. You will stick everything into that large cube, and the balance function then will have this small arm. Okay, so why is this useful? Because this is the key to prove the following theorem. And first I discuss it in R2, say, and then in how to implement it to the discrete case. And this is, as I mentioned, theorem of Koch-Sneddon and Weiss, and independently named from the 80s, 80 something, 86 maybe. It's a nice theorem. It says the following. But it takes a moment to realize it's not trivial. Then if P is a subset of RD, P set is 2 with positive upper density, then there exists a threshold, maybe depending on E, such that lambda is in the distance set of E, which I define in a second, for all lambda bigger than lambda 0. And the distance set is the set of distances between 2 points and E. So this set of x minus y, and x both x and y is in E. So in other words, any large distance realized between 2 points in E. The point is all large distances from a threshold. So you see it has this kind of structure that steers out some cubes in the space, each one a certain proportion. And then
so yeah, I got confused, but now I shouldn't be. So you use D for dimension and D for that distance set?
Oh, okay, that's true. How about
Thank you.
this way?
Okay, I mean for good.
So he basically says any two. Okay, so let me prove this using that observation. So basically, let's write a counting function for how many pairs of points you have at a given distance. Of course, it will be infinitely many, but with an integral. So let's see. Actually, so given, so E is given and lambda is given, so given lambda, let's define the following quantity and two functions, let's say f1 and f2, measurable on RD. Let's define n lambda, f1 and f2. So by linear, maybe I use p lambda to be the integral of f1x, f2x minus y, and e sigma lambda y, and dx. So what does it do? Well, you fix an x, where this is the normalized surface area. Imagine the sphere x equal lambda. So lambda minus 1, the that's lambda, the rest lambda is. So you take an x, you take lambda, you look at the sphere. So this is a convolution. This convolution tells you that you integrate f2 on this sphere. And then you integrate f1 x. Now, imagine that both f1 and f2 is the indicator function of a set E. And this is positive, so what does that imply? That means that there must be, so then the integral must be non-zero somewhere. Okay? And the integral is only non-zero at the point if x is in E, and that is another point y, a distance lambda, which is also in E. If this is positive, certainly the distance that contains lambda. Okay. So now, basically, what we want to do, so from the previous setup, we have our set with a certain density delta, and we will choose an epsilon, which is much smaller than delta, say smaller than delta squared, and we will have that threshold at 0, and we also have a large n. Basically, I will show that if I, in that situation, and lambda is bigger than L0, or maybe L0 times epsilon to the minus 2, then that distance is realized already in this part of the set E. And that would be enough because you can choose this an arbitrary large. So the thing is what we want to control this expression, which we decompose 1e into a constant, which is its average, plus a balance function. And from the constant, you get constant contribution, and the contribution from the balance function will be controlled by that one, which is small, and then we would be done. So let's do that calculation. Maybe it's this here. Right. So the first claim in general, this is the second lemma. So let's say now F1 and F2 are defined on this line to Q sub n and both bounded by 1. So the minus 1 and 1. Let's say lambda is essentially less than n. Maybe if the condition doesn't work out, I change it using the proof. But then the claim is that T lambda F1 F2 is bounded. Oh, an absolute value.
Sorry, what is Fn1 or what is that?
What?
What is F sub n1?
F1.
Oh, that's a one.
Yeah, so let's say
just the same as
two bounded functions, and then there is that bilinear expression, say T lambda F1 F2, and I want to say that if they are bounded, this is controlled by this U1 L1 of either of them. Wait a second, what do I want to say? Yeah, lambda has to be bigger, yeah. So I need some more parameters, let epsilon bigger than 0. And let's say 0 less than L less than epsilon squared, let's say, and everything is much smaller than n. Most parameters are much smaller. Then you have the following estimate. This is less than equal than the minimum of either F1 or F2. U1 L1. Did I put the here plus a constant times epsilon. That's the claim. Okay, so how to prove this? It's a nice exercise in Fourier analysis. It's relatively quick and easy because if you look at this expression, this is the inner product of F1 with the convolution of F2 with sigma lambda. So T lambda F1 F2 is, so if the y integration gives you a convolution and the x integration gives you an inner product. So you can write, if you go to the Fourier space, use punch around. So it's F1 f of c, F2 f of c, conjugate sigma under f of c. Okay, which for the normalized surface measure, you can write this as sigma hat under c. Normalized surface area measurement on the sphere of this lambda. All right, now how can I compare it to that kind of expression? So here I have a convolution with a measure, and here I have a convolution with the indicator function of a q. So I want to compare the two things to each other, so I do a trick. Now, maybe even before that trick, sorry. I think I should be a little bit careful here because this is not quite right because this is not normalized. So I should probably just stay with that loop right away here, and the x integration should be normalized. That's because otherwise, one expression would be always bounded by one and the other wouldn't be, so that would be a strange statement. So I always said, so this inner product, let's say, is also normalized in the X variable. So you always divide by 1/q. So let's define the inner product like that. Yeah. So be careful somehow with the normalization a little bit. Okay, so yeah, I think I can put in absolute values. So in this normalization, if both of them would be the same functions, it would be f1 hat absolute value squared. That would be just this quantity, which would be again bounded by 1. So we can do a Cauchy-Schwarz, and we can certainly say that you can estimate this by just basically the integral of f1 hat c squared sigma f1 c c. And then we decompose this further. So now we will embed, that is this normalizing factor everywhere, I think. But then what we will do, we will artificially embed the Fourier transform of the indicator function of the chi-L function. So basically, I will artificially compose this into two pieces. One is this, and chi-L hat c squared. That's actually that's a symmetric, so that's a positive quantity. Plus another term, well, what is left, then you would have one sigma hat lambda c times 1 minus chi-L hat c squared. Certainly true. So if you think about, okay, so how do you further estimate this term? Now this is a normalized measure, so this is less than equal than 1. So you can take this away and you still get an upper one. And what do you get when you take this part away? Well, this is just f1 hat times chi-L hat add to norm squared, and that's exactly the norm. Because that's the when you take this part away, because it's bounded by 1. And then for the second part, I think this forcing is bounded by something like epsilon, because this quantity is uniformly small. Let me explain why. That's what is used is the decay of the Fourier transform of sigma lambda hat plus 4 of epsilon. And why is that? That's because if you look at this quantity, which is again, it's a normalized bilated sphere, so you can write it either L c squared. So there are two possibilities. either one, so this is bounded by basically 1 plus lambda c to the minus 1/2 by the decay of the Fourier transform. So then if the first case, this quantity is already big, so lambda times c is bigger than epsilon to the minus 2, but lambda is much bigger than L, so if let's say c is bigger than epsilon to the, say, epsilon L, let's say 1 over epsilon L. So it has to be bigger than 1 over lambda, but 1 over lambda is much smaller than 1 over L. So this could be a little bit bigger than 1 over L. So let's say 1 over epsilon L. And which is bigger than, so what do I want? Let's see, bigger than say epsilon to the minus 1 over epsilon. So C is bigger than 1 over epsilon lambda. Let's just put this way, which is obvious. Then lambda c is bigger than 1, let's say epsilon squared lambda, then lambda c bigger than epsilon squared. So this term would be bounded by constant times epsilon. So this is the first case. And the second case is the opposite. If c is less than equal 1 over epsilon squared lambda, and maybe here I should change, maybe I should say that the word L is less than epsilon to the 4. Then C would be less than, say, epsilon squared over L. Because lambda is much bigger than L. And then L times C would be less than epsilon squared. So, but this is normalized, and this quantity is bigger, less than equal than L times C, times that constant, and then this quantity would be less than epsilon squared. Because this is chi hat 0 minus chi at c, because chi is normalized, the Fourier transform 0 is 1, it's a continuous Lipschitz function. So that because this is basically chi star chi, which is like this kind of function. So this is Lipschitz, so this is bounded. So no matter what is c, one of the terms is always bounded by epsilon. So this is uniformly bounded by epsilon. So then the whole thing is bounded by epsilon times the normalized to norm of f1, and if f is bounded, that is bounded by 1. So this is basically a norm which controls the count of distances, as long as the scale of the norm is less than the scale of the distances. And then basically the proof is done, because all is left now. So to prove the theorem at this point is.
Can I ask you just because I missed that part? So you in the first line of the proof, at the end you have this. You rewrote the inner product as as Fourier transforms. Using pressure, and then what did you do? You did
so basically
you did the Cauchy-Schwarz,
Cauchy-Schwarz,
but with respect to the measure sigma hat times d, or what? I mean, why don't we have sigma hat raised?
I mean, if you put an absolute variable there, then you can do it in different ways. You can do this to the 1/2 times to the 1/2, and then you do the Cauchy-Schwarz, you get sigma lambda hat pretty much everywhere. You can do it that way.
Sorry, what you erased what you
so indeed, when you put an absolute variable there, you can write this as itself to the 1/2 times itself to the 1/2,
and that's why you
you can for example.
So and then for the first one you use that it is less than or equal to 1 because of something.
Yeah, because it's a normalized count of the,
I see.
because it's a normalized surface area measure. And then the both integral in the functions are bounded, the measure of the sphere is normalized, and the measure in X is normalized, because you have this 1 over Qn, so everything is bounded by 1.
I see.
But when you use Cauchy force, that should be square,
Yeah,
Okay.
maybe you're right, yeah.
Okay.
Yeah.
Or
that's
the
fine.
left,
Yeah,
you mean,
Okay.
the left.
yeah, the one, the square will be bounded by that, so we get for the square is bounded by, but then it will itself will be bounded by like root epsilon as it want to matter, but yeah, it's that. There are different ways to do this, but so how to finish the proof after that? So if we remember the setup, what happened in our set is, now what, can I feel this? This calculation, so the language there. So now the proof of the theorem, if you put together, so there was a Line's theorem, is the following. So we had our set E, and now then we have these two scales. We choose an epsilon, so let's say delta by E. If delta positive, we choose an epsilon which is sufficiently small, say 1 over 10 delta to the 4, just to be safe. And then we have these scales. Then we have an L0 scale, which depends on our set, and then we choose N to be much larger than L0. But we will have this property such that if E prime would be the restriction of E to that large cube I was talking about, may be centered at some point, but this is a translation invariant question. Distances you can translate the set, and the translated will contain the same distances. So we can imagine that this cube is centered at the origin, this large cube, and then you choose its balance function, which is just minus its density on this cube, which I will denote by delta, some delta prime maybe. Then this function will have small u1 So now, but now, if we count the distances, so then for any lambda, which is bigger than, let's say, what we had epsilon to the 4 times R0, we can count the distances in E prime at lambda by calculating this expression E lambda 1 E prime, 1 E prime, and as it is usual in additive combinatorics, then you decompose this into 4 pieces. So each of the 1 E prime you write it as delta prime plus the balance. And this one too, so you get 4 terms because it's a bilinear expression. And then you use the constants. Since everything is normalized, you get the delta squared from this, or let me call this delta for simplicity. And you get a bunch of terms, but these terms are of the form, at least one of the term is Fe prime, and the other term could be either 1 E prime or Fe prime, some F. Terms like that, 3 terms like that. Yeah, but these are then actually bounded by the norm plus O of epsilon, but the norm is also epsilon, so all these terms are at most epsilon. And it's positive. So then, this way, you get basically all distances bigger then say this epsilon to the minus 4 times under 0, and epsilon was just the power of lambda. So some negative power of density delta times the threshold. And not just you get that, but you get this recurrence type theorem that actually, if you look at this count, it's almost delta squared. And so the set of points and distance lambda, the proportion of the set of points is what you expect in a random set of density delta, because in a random set you choose one point, there is delta probability and then you choose any other quantity, you have delta probability as well. So in some sense, you get this optimal count in your set. So this was the starting point, and of course, Bergain did this. So Kotzendon and Weiss use ergodics theory to prove this. And the proof wasn't that simple, and the reason why the proof wasn't that so simple is because the first time occurrence on this principle is not sharp. There is like an epsilon error in it. So it doesn't really work for sets, but you kind of have to take a delta neighborhood of your sets, and then you can translate between ergodic statements. And so that's why they have to work relatively high. Now, basically, since I took so long of a time to explain this, I have two options. Either just to tell you what kind of results follow from this, because I don't think. So maybe I make a note that this approach kind of works in ZB, and how does it work? Using that concentration of the Fourier transform to lattice points, and I just sketch like 3 lines about if I want to try to prove anything. And then I tell you what type of results this has started. I can mention a couple of results, which kind of what is called the geometric Ramsey theory or things like. Okay, so first on CP. So you don't have the exact amount on ZB, and that's because the integer lattice has sublattices. So on ZB, immediately, you can take P to be a congruence class mod Q. So let's say we fix on delta, and we choose a small q. Let's say Q is less than or equal to delta to the minus 1 over D. In other words, 1 over Q to the D is bigger than or equal to delta, and we are in Z. So then if you take your set to be just a congruence class mod Q, so some S plus Q Z to the D, clearly this set has positive density, has density 1 over Q to the D, which has density bigger than delta. However, it won't contain all large distances because because every distance is a multiple of Q, because this is just a transit of Q times E to the D. So Q lambda square is in N as usual, because the distance between two lattice points is the square root of an integer ZD. Okay, so then this theorem is not true. Won't contain all, but then with this modification it is true. So what is true in ZD again, b bigger than or equal to 5. I don't know why I bother to read. Anyway, so b bigger than or equal to 5, and then E is a subset of ZD. Of positive upper bound density, which is defined the same way, equal delta bigger than 0. Then there are two parameters. So then there exists as before a threshold, depending on E, but also an integer Q, which just depends on the density. And you can explicitly calculate this Q such that Q times lambda will be the distance set of E for every lambda bigger than or equal to lambda 0. So the difference is you have to multiply it with Q, but this Q will depend only on the density, and you can calculate it explicitly. It is the least common multiple of all Q's up to some negative power of delta. So how to change that argument a little bit? So there are two things here. What you want to avoid sets which are.
I'm sorry, I don't. We are talking about integer these differences, right?
Yeah.
Or what?
So, yeah, but so then of course, lambda square is in it. Because any distance among the integers.
Yeah, okay.
So
So that's an assumption.
Yeah,
Okay.
we always assume this on the discrete case. So there are two extra things. One is the void sets which are concentrated on residue classes, mod sum Qs. So you introduce a notion of uniform distribution mod Q. And you can assume right away your set is uniformly distributed because imagine if not. So what is uniform distribution? I say that E is, let's say, eta uniformly distributed. If the relative density, upper density of E on any residue class mod some Q eta, and this is the same Q eta we talked about last time, at least just a little bit bigger than the relative density of eta, let's say 1 plus eta, or some power of eta, how it comes out, anyway, times the upper density of E. So that Q eta is again the least common multiple of Q's up to some negative, I think that's what I used last time, some constant times the -2. So then we say it's uniformly distributed in an upper bound sense that it's one of them doesn't increase by just a very little on any residue class. Mod some big Q eta, but then for this is true for any Q divides Q eta because that lattice is contained in this. The lattice mod Q can be partitioned into lattices mod Q eta. So then, if on all of them the relative density is small, then it's the relative density is small on any Q. In particular, on any for any Q which is less than a constant times eta to the -2. So that's again the role of this taking the least common multiple. Now, is this important? Is this a very strong restriction? No, because imagine that this is not true. Then what's happening? Then you can pass to a sublattice and you have increased density of E on this sublattice. And let's say the statement is true for this increased density. I mean, the theorem is true for that increased density. So then on this sublattice, you will have all large distances. And then you just project it back to the original lattice, and it will be true also for all lattice, and you just change the Q a little bit, multiple with this Q eta. So that's a typical what is called a density increment argument. Because if it's not true, then you have increased density. And you apply your theorem. Let's say that you do an induction of the density and a discrete set of densities. One is just a fixed power of the other one. So you can assume that. Once you assume that, for these sets, the argument, you have the same result. So if this is true, then it will contain no large distances. If you have this property, that it does not increase on any sublattice, the density doesn't increase.
Sorry for stopping you. What is eta uniform distribution?
S is for any S. So this is
what is eta uniform? What is the concept?
The concept is that the upper density of the set doesn't increase on any sublattice you get Q. So that's I see. Yeah. So that's exactly the opposite of that counterexample, because that counterexample, the whole set is supported, whole set is living on one sublattice. Well, not sublet translate, one congruence class of ZD. And the other one is that no matter, it's kind of very similar if converted like the Ross theorem. I mean, Marius will prove it with ergodic theory, but if you see any proof of Ross theorem, it's basically either you can count, either you have the 3APs in yourself, or it has increased density in a progression. Instead of a progression, you have d-dimensional progression. But in this case, they are very explicit with an explicit Q. So basically, uniformly distributed mod Q, let's say. So you look at its density on any residue class mod Q, and it basically does not increase. That is your assumption. Then it's you can say it's very uniformly distributed, the residue class is not Q.
Mhm.
Once you have this, then you can run the continuous argument, and the reason you can run the continuous argument, you write down the same counting function. And under this assumption, you can set up the same argument. There is some scale L0 and some larger scale n, such that on any cube of scale L, again, the density doesn't increase much. So now, in the discrete case, when you want to do this calculation, let's say both of them the same, so then it would be a sum. So we are in the discrete case in x, in q, in x, fx, and then a sum in y at x minus y. And remember this sigma lambda y, which is now the normalized indicator function of the discrete sphere. So formally, it is the same kind of thing. So you have 1 over qn. And then you integrate in the torus, because the Fourier transform is on the torus, f of c squared, and then you have sigma lambda f c, big C. But now you cannot just cut this into 2 parts by separating the origin as before, but you have to separate all rationals, because this is only small away from rational points. So you need to embed a different type of function. That's exactly what we did before. So what you embed, not just the indicator function of a cube of size L, but the grid within that. So this is something like high Q of L. And then basically you embed this high QL at C squared. And then will be, if you be kind of remembering, something like a sum over all L in ZD of high hat L times C minus L over Q. That's the expression we get for the Fourier transform. Then you basically take the indicator function of this grid within L. And that is small. This is bounded. So if you take 1 minus of that, this would be smaller than L prime C minus L over Q for any L. So if I subtract this, then I'm away again from the rational points, or I get something smaller. So if I'm close to rational points, say this is less than epsilon, 1 over epsilon L, or epsilon over L, then this would be less than epsilon. But if that's not the case, then I'm away. If this is not true for any L, then I'm away from all rational points, and then I prove that the Fourier transform is small. So if I take this times the discrete Fourier transform, that again would be uniformly small, and then the whole argument works as before. So this is how you get implement this argument to the discrete case, and then you get this type of theorem. So the argument is essentially the same. You need an initial density increment argument, so you can, by induction, kind of the density, you can assume that you have uniform distribution of some large Q, depending originally on the density of the set. Once you have that, you can set up these scales L and M, such that you have this extra small oscillation property, and then you can embed this function, and then the error term would be small, and the main term would be again that norm which measures the oscillation, which is small because this is how the setup works. So, all right, so that's all I wanted to say about the discrete case at this point, because I took so much time trying to explain the continuous case. By the way, I did not explain well, because that's like a 2-page proof. If you write it down, continuous case, very short. Now, what surprising a little bit that essentially the same argument works to prove something which looks much, much stronger. So the Bernie not just proved this, but in his paper he proved the following result. So here, let's just number A, and instead of the distance set, you have the following. Almost like this. So let's start here. Let's say you have a simplex on K points, like regular simplex. On K points. Let's say K Germany plus 3, otherwise we just go back to the Coxners and Nice. So now, all right, and this is non-degenerate, so this is a general position. It's not true if you have 3 points on a line, that would be a simplex. This here. Okay, now let's say you have a subset of Rk, which is positive upper density. Then the following is true. Then there exists a threshold such that for every lambda, there exists a simplex delta prime contained in it such that delta prime is isometric to lambda to the dilate of, let's say, let's call it of delta k, so that's the simplex. So what does it mean? If this is a regular simplex, it means that, say, a triangle, that you have a regular triangle in E of side length lambda for every lambda bigger than equal than lambda 0. So what's the point? And that's true for any simplex as long as it's non-degenerate. So in the point, there's lattice points in general position. So for example, for this or for like this in 4 dimension and so on. So this is looks a much stronger result, and indeed Berlin called it a semi times here for subsets of Rk, but in fact the proof is almost as simple as the previous one, because that same simple U1 unknown controls the simplices, the frequency of the simplices at side length lambda, which appear in your set. And let me just show one calculation for triangles and the last thought. So now let's say you want to count simplices in a set or along a function. So you write something like E lambda F, let's say all the same 3 functions. And then you want to evaluate this quantity that evaluates all regular simplices of size lambda along F. So that would be an integral, triple integral. So fx minus, let's say, y1, and fx minus y2. And then, let's say you think the first one is x plus y1, x plus y2. So y1 has to length lambda, so d sigma lambda y1. But now y2 has 2 conditions. Y2 has to, so if you kind of think of just about y2 and y1, they look like this. So y2 has length lambda, but y1, y1, y2 has length lambda. So this is a sphere which it depends on y1. So you know it by d sigma lambda y1 and y2. And I mean, we can derive that. Let's see. Okay, so now I want to estimate this. So what do I do? So I pull out the y1 integration, and then I would have a d sigma lambda y1. And in this calculation, all functions are bounded by 1. So if I just want to estimate this from above, then I can pull an absolute value inside, and then I will have an integration in x. And if you look at this integral with that's a convolution, so I would have an x3 convolve with this sphere, which kind of depends on y1, because this is the third point, and kind of it has to, basically a regular triangle, it has to look like that, in a sphere which is orthogonal to the y1 direction. I pull in an absolute value, and then since every function is bounded by 1, I kind of forget the rest. But the x integration is normalized, so I can use a, and this is normalized, so then I can use Cauchy points. Of the integral of this square, which is the L2 norm, and if I use again Poincaré, that would be an integral in the Fourier variable, and I would have SV x d squared times this d sigma lambda y1 FC squared. So if I put the integration in y1 together, then I get some function of xi, which I denote by I lambda of xi, and that will decay just like the Fourier transform of the sphere. So we can embed the same kind of factor, because what this quantity will become here is an integral on the sphere. So d sigma lambda y1 times d sigma lambda y1 at c squared. So what is that? So what we do, we choose a y1 on the sphere, and then for each y1, we have this other sphere S lambda y1, and then we have the measurement, and then the Fourier transform of that. Now this is, since this two-dimensional sphere lives on this orthogonal plane, its Fourier transform is only decaying in the direction of the plane. So only in a certain direction, but when you average over y1, then because of that, it will decay in all directions. So basically, all the difference between counting triangles and distances is it's a little bit more complicated, but essentially we have the same law. So you can use the same argument as before to prove Bergain's theorem. And in the discrete case, if you write this out, this would be a double sum. And in the discrete case, you would have something like sum in y1, everything normalized, but in the sphere. So you would have y1 equal lambda, and then this is the Fourier transform, and the square, it's a sum, let's say z, but z has two, or y2 has two conditions, so its length is lambda, and y1 minus y2, length is lambda, and then you would have something like e to the 2 pi I y2, that's c, but you square it, so you would have the same sum with some y3. And this would be the Fourier transform of some surface determined by a bunch of quadratic equations, because you have a lot of restriction to y1, y2. So basically, evaluating at something like, so this would give some omega lambda hat in the big space, evaluating the 0 c and negative c. And what you write down, the condition, the restriction y1, y2, kind of gives you this configuration, so you have 0, y1, y2, and y3. So now this is where the theory of Diophantine equation comes in, because now you have a surface on the big space on z to the 3b, because you have three variables in z to the b, and which is defined by these quadratic conditions, of course. This is how we look at in ZB. And then basically, you take the Fourier transform, the lattice points on this big surface, and evaluate it at some point. And all you need, again, is that the Fourier transform is concentrated in rationals, because then you can embed this higher factor, and then you can run the argument. So you get this, so you get an analog of Bergain's theorem in ZB. So these are the easy theorems, so to speak. Once you look at configurations which are also linear relations like rectangles, then you kind of have to mix a little bit method of additive combinatorics and Fourier analysis. Then it becomes much harder, or in case you have like 3 points in a line, you want to show that all large distances appearing between them. That's not true in ordinary Euclidean distance, because if you change the distance to some L4 distance, it becomes true. And only one last remark, to prove that in RD, the first time we could prove it in RD was using time frequency analysis. Basically, you can reduce this to somewhat linear operator, which is much more complicated than this one. But fortunately, there's the theorem of the Christoph Thiele, Muscalo, and Tau, which kind of covered it. And that approach has been expanded by Pomona Dolcik and Rekord Kovács. They proved a lot of theorems in these directions in RD, and the question is how to implement those results in ZD, because I don't know, or I haven't seen using time frequency analysis on that response, so we need a different approach. And I wanted to talk a little bit about that, but I was too slow today, so I start showing.
So let's thank Ákos for the very nice series of lectures. It's time for questions or remarks.
Yes.
So a couple of questions. Like the first is when you had the one simplex, I mean the distance.
Oh, the one simplex, yeah.
Then you were asking the dimension to be greater than 2.
Yes.
Greater or equal than 2.
Yes.
So when you have the K simplex, you also have the dimension greater or equal.
Yeah, but the one simplex is 2 points, so the K simplex is K points, so it's K minus 1 dimensional. So yeah, and that is an open problem, because you can have triangles in the plane. And is this true for subsets of the plane, that even you have regular triangles at all large scales? This actually goes back, because the starting inquiry was by these ergodic series. I think this goes back to Fürstenberg's question: is this true in the plane? That if you have a subset of positive density of the plane, then you have, say, regular triangles at all large side lengths, and this still not found. This argument breaks down because then the third point is fixed. You can't average, and that's essential in these arguments, that you have a little bit extra freedom to average. But then it is like Ross theorem, but a harder version of Ross theorem. So it is true, and it is basically the Ross's argument tells you that there are arbitrary large regular triangles or corners, or whichever you want in the plane, because it's basically you can parameterize some x plus y, x plus r of y, where r is a rotation. This is just a two-dimensional version of a CAP, like x plus y, x plus 2y. So instead of the one-dimensional group, use the two-dimensional group, but Ross argument the same. But what is not known whether this is true for all sufficiently large side lengths. So Rossian tells you there are arbitrarily large regular triangles, but you don't know whether there are all large triangles. And so yeah, it's a good question, and that's open. Yeah. Now, of course, in ZD you need to go higher dimensions, because I mean you can't lattice points on like this complicated surface determined by a bunch of quadratic equations. So the dimension is still linear, but you need a very sophisticated theory of quadratic form even to show that you have case indices in subsets of ZD where D is something like 2k plus 4. But that's already using a lot of calculations and development in the theory of quadratic form, that you can count lattice points on these surfaces in those dimensions. But yeah,
sorry, so I because I didn't understand the question exactly. So you were asking that depending on K, what could be the dimension in ZD? Yeah. And you said that it is 2K plus 4. Is that what you said?
No, in the discrete case, but in the continuous case, it's K.
I understood, but in that's what his question. His question was about ZD.
Is whether you can do K minus 1 dimension, because the K simplex fits into the K minus 1 dimension.
Oh, I see.
So why do you have this discrepancy? And that's the reason, because then the last point becomes rigid. If you are in K minus 1 dimension, that changes the whole. That's an extra linear relation, and then it becomes a much more problem. Or even higher than simply a non-linear relation, but it's fixed. Another similar question is in the setting of sets of Hausdorff dimensionless than full. So there's the famous four-corner distance problem. And then what if you change Falconer distance problem asks what should be the dimension of the set in R2 so that the distance set will have positive Lebesgue measure. The conjecture is 1.
That was fast. Say this again.
So the
Slower.
Falconer distance problem
Yeah.
is the following. Take a subset of E of Hausdorff dimension S, where S is less than 2. How large S should be so that the distance set, which is a subset of the real number, will have positive Lebesgue measure.
Oh, I see.
And the conjecture is 1. And it was a long, so Falconer himself proved 3.5. Then 15 years later, Tom Wolf proved 4/3. And now Goose and others using a lot of theory 5/4. But you can ask the same question for regular triangles. What should be the Hausdorff dimension of a subset of R3, at least, so that the side lengths of all regular triangle in E will have positive Lebesgue measure. And we could prove that there exists some threshold, but we couldn't get anything explicit, and we don't even know what to conjecture. It's very fun in that setting, it's not clear even what to conjecture. So that's wide open if you expand the Falconer distance problem to this situation where you want to find certain patterns. So that's another.
So in R2 it is still unknown.
Yeah.
The original.
Yeah.
No question from Max?
You have, not like, in the discrete theorem, you are only, I mean, yes, or at least you say it for D greater or equal to 5, right?
Yes, even for the one dimensional, yes.
Yeah. So if you, I mean, if you substitute your sigma lambda with this other sigma lambda with sigma lambda and more.
Then you can. But I think even more, but this theorem can be true in actually 4 dimension.
Right.
With the original sigma lambda. So I think, although because you would say a multiple of Q. I think it might be true with even in 4 dimension without. But then in general you get much closer to the continuous case in the dimension condition if you start modifying the discrete figures. So I mean that's another way of another type of question one can consider. The discrete case, what is really interesting is there is a recent result of Kovac, which is a very nice result in this line where you can put, so you have a subset of R2, and then you have a d-dimensional cube in the following sense, combinatorial cube, say that just like a rectangle, let's say, on the plane, but all side lengths is 1. And he could prove that a subset of the plane can contain this kind of pattern, which is like a hypergraph, but each edge has length lambda. And for any dimension, arbitrary large combinatorial cube on all large scales, you'll be just in a subset of the plane. And again, here you have a little bit of freedom to move this because you can, so 2 dimensions basically just this. So a rectangle 4 points, the rhombus. And it's 3 dimension to 3 dimensional rhombus or 4 dimensional rhombus. So all these things, all these patterns you can find sort of positive density of all large side lengths. So now to prove something like this extension is indeed, that I think is a very interesting question because these are patterns which on the one hand without restriction on they're already interesting. And these are controlled by this higher version of this local norm. So there's this Gauss norm that you can find the local version on RD, and these are controlled by those norms. You can show that. So you can start using some theory from additive combinatorics, so what is called the Fourier analysis, combined with the Fourier analysis of the Fourier transform theory. So, yeah, so there are lots of questions in this regarding this.
Questions? So let's thank again, Ákos.